Yeah, you're there. Good.
Are we live?
They should be live now on YouTube.
By the way, Claudio, yesterday I just received an email from, so we have this national funding agency, IPSRC, which is engineering science, where we usually apply stuff for, and they have a specific call for, let's call it Sandpit, where they're looking for ideas, and the name is specifically Reservoir Computing for
Oh, really?
Wow. DSTL, which is the defense kind of and military kind of approaches, but specifically reservoir computing. I was really surprised to see that because there are not too many people doing reservoir computing in the UK, I think. So it's good. It seems to be, it's on their radar. It's going to be a big thing.
And what, because the audio is not really perfect, I think. I couldn't really understand every single word. So, but it sounds really interesting. And maybe if you can maybe later on. Yeah. Yes, would be nice. Thanks.
Yeah, not sure. There you go.
We'll go online as well now?
Yeah, we're online now.
Going to record as well?
Yeah, recording on Teams already. We can cut it down afterwards. Yeah, should be. It should be.
Yeah, I think it's fine.
Good. Right, hello everyone, and welcome to our second to last MorphoTalk of 2025. Today we're joined by Claudio Gallicchio from the University of Pisa to talk about non-dissipative reservoir computing. Thank you for coming and talking with us online today. I'll let you take it away.
Thank you so much. Yes, let me start. Okay. I guess you can see my screen, and in case, just scream. Okay, thank you so much for inviting me, and it's my pleasure to tell you a little bit what we're doing in Pisa about reservoir computing and what we believe are the current limitations of reservoir computing and how to overcome these limitations with a few works that we're doing now. To start, I would like to first say that these slides are available online, so if you want to check them even after the talk, then you can find them online at this link. And my purpose for today, like I said, is to introduce a little bit the work that we're doing in our group at the University of Pisa. And to start with that, I would like to introduce the core concepts of reservoir computing. Probably some of you, or maybe all of you, are familiar with that for the work that you're doing and your research interests. But I'd say for the sake of a short introduction, maybe let me bore you a little bit with these details. Okay, so first of all, let me start by putting away this concept that the time series and stream data analysis is very important in general in information processing and in computer science because it has a lot of applications like the robotic applications that probably you are very familiar with, but also more, let's say, broad applications even outside of that domain, like the Internet of Things, cyber physical systems, language, of course, and human monitoring. And when we deal with the concept of streaming data and the concept of temporal data processing in with neural networks, then the model of choice and the starting paradigm, of course, is the one of recurrent neural networks, where you can have a lot of variants, but basically you have two core components. One component is the recurrent layer that computes a state transition function, where you create a latent representation of your input time series. So you create a state that is a nonlinear function of your input and the previous state. And on top of that, you put an output layer or a readout layer that computes the output based on the current state h of t, or the, let's say, latent representation of the whole sequence up to time step t. So this is very flexible, and of course it has been used and modified in a lot of ways. The core idea, anyway, is that all of the parameters, the weights, the neural network weights that modulate all of these two functions, the state transition function for the recurrent layer and the output function for the readout layer, are trained end-to-end by backpropagation through time. And when you train by backpropagation through time, a recurrent neural network, but in general, any kind of complex neural network algorithm, then you're going to need a lot of compute, therefore a lot of energy, time, and at the end, money, because you have to pay, of course, the energy for those computing requirements. Okay, so, yeah, so another concept is that because of this, training a recurrent neural network is difficult, not just because of the computing requirements that are there, but also because a couple of tricks and, let's say, aspects of the computation that need to be taken into consideration. So the idea, the general idea, when you have a recurrent neural network operating on a time series kind of data, is that you have this architecture, the simple vanilla version of a recurrent neural network that I showed you previously. You initialize with some initial condition, like at the origin of your latent state space, and then at each time step you unroll and you repeat the same architecture, so the same transformation across the input time series. So when you have, let's say, the first time step, you calculate the first hidden representation and the first output, and then the second input comes, and then you, based on H1, you calculate H2 and O2, and you continue in this way until you reach the end of the time series. So this process entails a couple of difficulties. And the first difficulty is related to the potential instabilities in this forward propagation, the forward propagation of the input signal across all of these nonlinear transformations. And the point is that, let's suppose, let's say for the sake of discussion, that you want that at the end, let's say here, of your time series, here your output is computed in such a way that the output depends not only on the recent inputs, let's say X4 and X5, but also on the previous ones, like maybe the beginning of the sequence. So X1 should be present in this H5. And because of this sequence of nonlinear transformation, think about like hundreds or thousands or maybe millions of these type of nonlinear transformation, not just 5, like in these slides for the sake of convenience, then you can have problems in this propagation, and then maybe the information can vanish over time or can explode over time, because maybe this transformation involves, let's say, very large matrix multiplication, let's say, and then maybe from a dynamical system perspective, this propagation of the information can be unstable, right? So a tiny perturbation can determine a very big difference and maybe an explosion of the difference across a long time horizon. Not only these instabilities, potential instabilities in the forward propagation, but of course also in the backward propagation, because, you know, when you have to train a very deep neural network or a recurrent neural network, which is equivalent in this case, here essentially you have one time step. For each time step, you have like the repetition of the same neural layer, right? So if you have 5 time steps, then it's like a deep neural network with 5 layers. If you have hundreds of time steps, then it's like having a deep neural network with hundreds of layers, right? So we know that backpropagating gradients through very deep neural networks can be complicated because of a similar problem than the propagation of the input information. In this case, you are propagating backwards the gradient. So again, the gradients can vanish because maybe the transformations involved by propagating the gradients will, let's say, be very dissipative, or the process can be unstable again, and then your weights, the weights in the neural network can explode, and then you will destroy your neural network. So essentially, the point is that it is difficult to have a recurrent neural network that propagates well over long temporal spans, so long-range propagation of the input, but also train the recurrent neural network on long-term dependencies, right? Okay, so historically, in the neural networks community, we needed to transit from the standard vanilla recurrent neural network cell operation in the left part of this slide into something more complex like the gated architectures. This is exemplified by the LSTM cell, which is very popular. Okay. The point is that when you accept this transition, you need to increase a lot the number of operations that you need to perform. Like you can see, the second line is the, all of these equations are the equations of an LSTM cell for every time step, and you can identify here the second line is the equivalent of a recurrent neural network in the vanilla formulation a few slides ago. All of the other equations are added, so extra compute, let's say, and all of these, let's say, underlined matrices or vectors are added as a parameters to be trained. So once you wanted to, let's say, save in a sense, solve the problems of the propagation of the information and gradients in the operation of a recurrent neural networks, now you need to pay even a higher price in terms, again, of compute, energy, time, and cost. So sometimes you want to pay this price, sometimes maybe you don't need to pay this price, right? And maybe sometimes you even actually cannot afford to pay all of this price. Like, for example, when you want to have an embedded application, or you need to have an embedded application, maybe the data comes from sensors and the compute should be performed on a Raspberry Pi or, let's say, any other kind of edge device where actually maybe you can do the inference part pretty easily of your recurrent neural network, but you cannot actually very easily do the training phase, right? Or this can be extremely slow. So that's a perspective under which reservoir computing has been proposed a few years ago. And here there is a very popular book edited by Kohei Nakajima and Ingo Fischer about reservoir computing that I really suggest you as a starting point if you like the ideas about reservoir computing that I'm going to tell you later on. So what's the basic idea? The basic idea is that instead of applying all of these training in my recurrent neural network, I try to use as much as possible the intrinsic computational capabilities of my recurrent neural network, even before or in absence of learning of the recurrent connection. So even before or without the backpropagation through time application. Okay, so we move from this situation of a vanilla recurrent neural network where all of the weights here, this WX, WH, BH, WO, and BO are fully trained in an end-to-end fashion by backpropagation through time. We move to a reservoir computing echo state network approach, where actually we look at the recurrent layer. We call this now a reservoir layer. And we look at this layer not under the perspective of a fully trainable neural network system, like to be trained blindly with backpropagation, but under the prism of dynamical systems. And we study this equation here, the state transition function equation, like a nonlinear input-driven iterated map or dynamical system. So the crucial part is that these weights indicated in green here, so all the parameters of the state transition function of the recurrent component of my system now are left untrained after the initialization. So this is the crucial idea. And the point is actually that we replace the full training of the recurrent component of the architecture with a smart reservoir initialization. So I just said we randomize the weights inside of the recurrent component of the neural network. But that's not only about randomization, it's about like having a state transition function that is that follows some dynamical system properties and essentially implements a stable dynamical system. So what we want actually here is that the state, this h of t that evolves over time, is not sensitive to tiny input perturbations, right? So it's a fading memory in a sense. So how to do that? Typically in reservoir computing, what you do, you control, let's say, the eigenvalues of the recurrent weight matrix WH, or let's say the spectral property more in general, like the maximum singular value or the spectral radius, like I said, and in general in application, you control the spectral radius. And this is indicated typically with this rho of WH, and there are in the literature, very long story short, a few theoretical results. And this condition that I indicated here is a necessary condition for the stability of the reservoir dynamics. That actually is telling us that if we control this quantity and we have that this quantity is smaller than 1, then in most of the cases the neural network will work properly, right, in a stable fashion. Then how to realize this in practice? It's very simple. For example, you can start with a random matrix. WH is a random matrix. Then you rescale the elements in the matrix in order to have the value of the spectral radius that you want. This is a linear property, so you can just divide by the spectral radius of the random matrix and multiply by the value of the spectral radius that you want. Or maybe you can use random matrix theory and you can, let's say, decide that you want the weights within a specific, you initialize the weights within a specific, for example, uniform distribution. And let's say you treat this desired value of the spectral values again as a hyperparameter. So anyway, the point is that you control the hyperparameterization of your layer rather than doing the training completely, right? So looking again at this equation, it is, let's say, the state transition function of your recurrent neural network. The most care should be placed into the initialization of this WH matrix. So you typically initialize randomly or in a fixed way, and then you rescale the spectral radius to the value that you want. Similarly, you can do an initialization of the input weight matrix, WX, like, let's say, controlling the magnitude of the weights. And the same thing can be done for the bias vector. Again, can be initialized randomly with weights within a certain distribution, and you control the magnitude of this distribution. Okay, so the point, after all, what you want to ensure is what is called the echo state property. What you want to check is this echo state property, which means actually that your reservoir, the recurrent layer, is implementing some sort of non-exploding dynamics, so stable dynamics in the long run. And here I give you a couple of examples just to give the intuition. In the case of absence of inputs, let's say autonomous dynamics, just to simplify the description, in the case in which you have this echo state property, it means that it doesn't matter what is the initial state of your system, like the red, the blue, or the green one. After a transient, the system will converge to a unique solution, let's say a unique trajectory, if you have the input-driven dynamics, or in this case, let's say you don't have input, so you converge to a unique solution that is the origin. So in any case, you synchronize the behavior of the recurrent layer irrespectively of the initialization in the initial conditions of the state. On the other hand, if you don't have this echo state property, then what can happen is that your system is sensitive to the initial conditions, or equivalently to input perturbations. And what you have is actually that depending on the initial conditions, or because of input perturbations, then your system can diverge to different solutions or different behaviors, even with the same input. Okay, so here in this plot is without input, but I mean, if you include input, then you will have different trajectories depending on the tiny perturbation that you applied or the initial conditions that you considered. Okay, so the approach is intriguing because, of course, it's efficient. You don't need to do learning at all in the recurrent connections. And maybe sometimes you can lose a little bit of performance when you work with real-world applications, like in this case, it's like human monitoring applications that I'm reporting here, like you achieve like 0.93 accuracy with reservoir computing stuff. And maybe with fully trainable systems, you can reach a higher accuracy, like 4% more accuracy. But the point is that you save a lot of computation because you don't need to train the recurrent components. So training is more or less thousands of times faster and thousands of times more efficient in terms of energy consumption. This is measured on a GPU application. Of course, it's unconventional and has been considered, let's say, as a paradigm for implementing neural networks also in hardware, because actually the reservoir, the dynamical component, can be implemented in software like we do in PISA, for example. But of course, essentially what it creates is like a latent representation that is some sort of, let's say, the state of a dynamical system that can be perturbed by an input, and there's some sort of fading memory and some possibility of having nonlinear representation of the input. Then actually you can replace your software implementation of the reservoir with a physical substrate that provides nonlinear dynamics. And this has been studied in several fashions, like in neuromorphic hardware implementations, photonic, memoristive, spintronics implementations, etc., but also in morphological implementations, also using the skin of a soft robot for doing the computation. So here there is a work by Koei Nakajima and Helmut that try to use this arm of a soft robot, let's say it's the arm of an octopus, that performs the operations of the neurons inside of the reservoir. It's very interesting because actually the input to the reservoir is encoded by the movement of this motor to the left or to the right. And then in the water tank, you have this soft robotic arm on top of which you have some sensors, and these sensors becomes, because of the movement in the water, become, let's say, the representation, the latent representation of the input history inside, computed by the skin of the robot that is moving in the water. And this is very interesting and can actually also be used as a paradigm in general, as a reservoir computing paradigm in general, to solve also real-world problems in robotic environments. And we have a few experiences of doing this in some European projects. And this one is for the Rubicon projects a few years ago, where actually we demonstrated the possibility of implementing this very simple reservoir computing neural networks on a small device, actually on top of a sensor that is placed on top of this robot that is moving in a wing of an hospital and is receiving these beacon packets from other sensors similar to that one that are placed in the environments. And based on the received signal strengths, the Echo State network that is placed on top of the robot here is able to localize XY, the robot in this case, in the hospital wing, providing a secondary localization system that can be used for recovery. So the approach is interesting and has, let's say, some robotic applications. But why does it work? That's a very important question, of course. And understanding why it works can also uncover some properties of recurrent neural networks that are intrinsic to the way in which recurrent neural network works. And maybe understanding these ways in which the recurrent neural network works without learning of the recurrent connections can open the way to creating different types of neural networks that maybe don't have the same limitation. So we call this the architectural bias of a neural network model. That is the type of computation that can be done by your neural network even before the learning, the training of the internal connections, right? So what is the architectural bias in general of a vanilla recurrent neural networks, right? So your vanilla recurrent neural networks originally is initialized with some small weights. And when you actually initialize your recurrent neural network with small weights, you create a state transition function that is a contraction. And this leads to what is called Markovian state space organization, which essentially means that your recurrent neural network, after the initialization with small weights, is already able to do something, right? And the something that is able to do is separating the input sequences based on the suffix of the input sequence, right? So suppose that you have a few, let's say 4 input sequences. They can be different, but in couples, they share the same suffix. Like the last part of the sequence is the same for these blue sequences S1 and S2, so they share the same suffix, the blue suffix. Similarly, these other S3 and S4, they share the same red suffix. Before that, they can be different, right? So what I'm saying is that the recurrent neural network, before learning, will be creating a latent representation that maps the input sequence into states that are close to each other proportionally to the length of the common input suffix, right? So the blue ones will be mapped to close points in the latent reservoir, in the latent state space representation, and the red ones, again, close to each other, but far away from the blue ones, right? Okay, so this is exactly the same characterization that you're using with reservoir computing or echo state networks, because you're using actually state transition function that is constrained to be stable, and this is very much linked with the idea of, let's say, contractivity, right? So you're actually implementing a contraction mapping in the reservoir. And if your problem is this characterization that depends on the suffix, right? So is akin to this Markovian state space organization, then the learning problem is now translated is moved only to the output layer, to the readout. So what does it mean? It means that the readout is typically a linear system, right? So I want to put a line into this new space that is able to separate the sequences. So if my problem is amenable to this kind of representation, because, for example, these first 2 sequences are positive and these other 2 sequences are negative, then it's easy for me to find, let's say, a linear readout that solves the problem, right? So the problem maybe was difficult in the original space, but now I mapped it to the reservoir space that organizes the representations based on this Markovian state space organization, and there I can find a linear solution, right? Okay, what happens then instead if my problem is not in agreement with this Markovian state space organization? Maybe these 2 sequences are one negative, one positive, and similarly for the other 2. In this case, it's much more difficult to find a proper, let's say, linear readout that solves the problem, right? So what does it mean? It means that because of this stability that I am enforcing also this contractivity, and this contractivity gives me something for free, which is the ability to separate the sequences in this case, right? So I can use the reservoir computing systems when my problem is in agreement with this characterization, which luckily happens a lot of times, for example, in when your data comes from sensors, right? Like, for example, I want to apply these ideas to human monitoring problems or, I don't know, robot localization, for example. But when your problem goes more in this direction, then maybe the reservoir computing stuff is actually not really properly utilizable. And this also happens a lot of times, for example, for language, when the suffix of maybe your sentence that you want to classify is actually not carrying whole of the information, right? You want to be able to keep track also of the beginning of a sentence, right? In language applications, you don't want to only focus on the suffix, right? Okay, so this is the Markovian bias, which is, let's say, a characterization of the way in which reservoir computing neural network works, that tells you what are the properties, but also what are the limitations. And within these limitations, there exist several architectural variants that try to, let's say, push the limits to these limitations. One, for example, is the cycle reservoir that was popularized by this work by Rodan and Tigno on minimum complexity echo state networks. And in this case, you organize your units to form a cycle, and this is interesting because actually your recurrent weight matrix has a very clean structure with non-zero elements below the main diagonal and on top right. And I mean, you reduce a lot the degrees of freedom in the generation of these metrics because maybe you can only have one number here, which actually is also the spectral radius of this matrix. The construction can be deterministic, and you have, let's say, an orthogonal organization of the linearized version of the dynamic. So you can have, let's say, good short-term memory in the reservoir system. And another idea is the one of deep organization of the layers inside the recurrent neural network. And this is a work that we have done in collaboration with Alessio Micheli and Luca Pedrelli a few years ago with the, let's say, popularization of this deep reservoir computing idea, where instead of having just one reservoir layer, you have multiple layers, one on top of each other. And let's say, instead of having one layer, you have a number of layers where the input from, let's say, for the ith layer comes from the state of the previous layer, right? So the first layer is driven by the external input, and successive layers are driven by the output of the previous layers, the state of the previous layers. So, I mean, you can study this as a nested set of dynamical systems with a lot of properties like a longer, shorter memory, a longer, let's say, multiple temporal scales, multiple frequencies, etc. Still, though, with this fading memory characterization. Also, interestingly, you can, like I said, you can map these ideas into neuromorphic hardware, and I just want to mention a few of them that that pertain to the work that we've done in collaboration with other people in Europe. And one is this hardware-friendly deep reservoir computing system that has been published this year with Miguel Soriano on neural networks. In this case, we take inspiration from the, let's say, hardware of time delay nodes. And another one is a collaboration with a nice bunch of people from the University of Pisa and the Polytechnic of Turin, where we use we create a version of a recurrent neural network also in the reservoir computing area that is inspired by the dynamics of memory state devices. And another one that we have studied in our group is what we call the random oscillator network, which is a collaboration between the University of Pisa and Technical University of Delft, where we create a version of a reservoir computing system that is, let's say, inspired by the dynamics of heterogeneous oscillator. So you have two components. You have an excitation layer, which has, let's say, the dynamics of a conventional echo state network. And after that, you have, let's say, a force mechanical oscillator that carries the information properly across time. Okay, this said, like I said, reservoir computing and some clearly as some characterization, what I said, the architectural bias, and some limitations, right? So especially in the last 10 years, at least, the landscape of sequence modeling has changed a lot. And nowadays, when we want to talk about deep learning applications, of course, you have transformers, right? The undisputed kings of sequence modeling. Why they work very well? Because of several reasons, but especially they are capable of an effective long-range propagation of information across different parts of your sentence, right? This is mostly used for sentence processing, language processing. And another type of models that you have nowadays is the state space models like S4, S5, Mamba, linear recurrent units, and variants. Here they actually strike essentially because they are fully trainable systems that are based on linear recurrence, and being based on linear recurrence, they can be parallelized in training. So they in a sense can be considered like a challenge to reservoir computing, because if you have a GPU at your disposal, then you can parallelize the training across all of your time steps together, right? So it's another version of a recurrent neural network system, but more efficient in terms of training, right? And what is the position of reservoir computing here, right? So concerning long-range propagation and transformer challenge, still very far. Concerning the state space models type of algorithms, actually, we are still very efficient as type of models, but let's say the efficiency gap, is much more restricted in this case because of the efficiency in training of these new type of systems. So, talking about at least the first kind of challenge, so the possibility to challenge transformers, right, or transformers-like models on long-range propagation. The idea is that actually reservoir computing systems, they are not able to perform this long-range propagation of the information because of the fading memory, right? This is one of the aspects that I mentioned at the beginning of my talk. So the input information injected in my recurrent neural network at a certain point during my operation of the recurrent neural network will be discarded after a few time steps. This can be hundreds time steps, but at a certain point this will happen, right? So the input information will tend to vanish over time, right? So long-range information propagation is very difficult with conventional echo state network because essentially of this requirement of the echo state property that we are considering, right? So we are imposing that our system should be stable. In order to be stable, in practice, it will implement a contraction. And because it implements a contraction, then it will tend to forget progressively old parts of the input sequence story, right? So this is one of the main challenges that we considered in our group in the last years. And what I want to present briefly is a few alternatives to the conventional echo state network that we came out with in the latest years. The first one is a generalization of the echo state network, or reservoir computing more in general, that we call residual echo state network, or RESESN. This is a work that I performed with Andrea Ceni, which is a nice researcher here in Pisa. And the basic idea here is to introduce orthogonal temporal skip connections that change the architectural bias that I mentioned at the beginning. So on the left here, you can see the basic idea, the basic vanilla formulation of a recurrent neural network and also of a reservoir computing neural network, of an echo state network, when we focus on the untrained reservoir layer, the one that we don't want to adapt with backpropagation. Okay, so in our proposal, we expand this untrained reservoir layer in the way in which is represented to the right of the slides. Right. Okay. So I'm going to go a little bit more into the details. The formulation of the state transition equation is modified by a term that carries these linear orthogonal skip connections that changes this architectural bias. All right. So first of all, this green part in the equation is the reservoir of a conventional ESN-like system. So conventional reservoir computing. Right, this part in green, which is also this part in green in the computational graph. The new part that we add is very simple but very effective. Is the blue part here, which is, let's say, also indicated in blue in the computational graph on the left. So what we are adding is this temporal residual connection that the idea is to create a path for the long-range propagation of the input. So across these connections, the input can be propagated from very distant parts of the input sequence in the past to, let's say, the current time step in the operation of the recurrent neural network. And this is modulated by an orthogonal matrix O here that can even be generated randomly, but should be orthogonal and should be orthogonal in order to give, let's say, a tunable proximity to what is called edge of chaos or edge of stability dynamics. And to be a little bit more precise, I would like to at least give an intuition of why these propagates better the information by studying this equation and by considering the Jacobian of the bias-free autonomous system version of it, right? So to simplify a little bit the discussion, suppose that we consider 0 input to our system and 0 bias. So we are neglecting this right part of the equation, right? But this is just to understand the architectural bias. The idea is the same when you consider the input, but the mathematics is a little bit different. Okay, so if we consider the Jacobian of this system, in this case, it's composed by 2 parts, right? The first part is given by these skip connections that we have added, and actually gives you, let's say, the characterization of the eigenvalues of this Jacobian to be distributed across over a circle in the Gaussian space of radius alpha, right? The second part gives, let's say, a sort of perturbation to this nice distribution of, let's say, maximum, let's say, magnitude given by this beta times the 2 norm of the recurrent weight matrix WH, okay? So overall, what does it mean? It means that by just adding this left part here, we move from very strict fading memory dynamics, which means like the eigenvalues distributed within the unitary circle, to a distribution of the eigenvalues of the system within a beta norm of WH tube around the circle of radius alpha. And this means actually what is indicated in this slide, right? So your alpha gives the proximity to the edge of stability. Maximum proximity means alpha equal to 1, where you have, let's say, your eigenvalues exactly around the unitary circle, on the unitary circle. And this beta and WH give you the perturbation to this position, right? So overall, there will be a tube that is thick in a way that depends on beta and WH around this circle. So this gives you, let's say, the flexibility to have both the conventional dynamics of an echo state network, if this alpha is equal to 0, for example, or is very small, and also the possibility of operating very close or tunably close to the edge of stability. How close depends on just one number, this hyperparameter alpha. And of course, in applications, we can see that there is, let's say, a very big impact of this, especially on regression tasks, where you need both memorization and nonlinear processing. And the second approach that I want to put forward is this approach that I called the Euler State Network, which is one of my solo works. Here, the idea is that I want to give away from the echo state property, and I want to create a recurrent layer that absolutely doesn't have this fading memory, right? Without fading memory, but still in the reservoir computing realm. So what can I do? I can start from an ODE version, so continuous time version of the equations, and then the state transition function that you can find here. And then I can observe from control theory that if I impose that this recurrent weight matrix is antisymmetric or skew-symmetric, no, then the Jacobian of this ODE has eigenvalues that are exactly on the imaginary axis. That means for continuous time dynamics that I am exactly at the edge of stability. So I am non-dissipative, okay? Okay, so I start from this observation, I impose antisymmetric recurrent weight matrix, and then I discretize using the forward Euler method in order to have, at the end, this equation. This equation would replace the state transition function of a conventional echo state network, the one that I showed you at the beginning. And now you can see actually that this component here, the recurrent weight matrix, is a little bit different. Now we have this WH minus WH transpose that is by construction antisymmetric. And then you also have a few hyperparameters that you need to consider. One is the step size for the discretization, and the other is the diffusion for the stability of the forward Euler. But then you can even leave all of the parameters untrained, like in reservoir computing, because this system will exhibit non-dissipative dynamics, edge of stability dynamics, irrespectively of the individual weights that you will put here and here, right? Because, like I said, the characterization of being non-dissipative depends on the structure that I have applied to the recurrent weight matrix, not on the specific weights that are there, right? So you have non-dissipative dynamics and, let's say, proximity to the edge of stability by architectural construction. Because I changed the way in which the state is computed, now I don't have anymore the architectural bias of being with fading memory, with, let's say, the suffix-based organization that I mentioned at the beginning. Rather, I have this edge of stability bias in my system. And again, this can be seen if I consider the Jacobian of the bias-free autonomous system. In this case, I have two components. Again, one comes from this HT minus one and let's say the one minus the diffusion times the step size component, which is giving me the real part of the eigenvalues. And the other part comes from the antisymmetric part of the state transition function that gives me, because this has imaginary eigenvalues, this gives me the imaginary perturbation to the eigenvalues of where the real part is 1 minus this small quantity, right? And in general, these epsilon and gamma are small quantities. So in practice, what you can see is that your eigenvalues of this state transition function are concentrated on, let's say, one vertical line in the complex space, where, let's say, the real part is like 1 minus this gamma epsilon, and gamma epsilon are typically in the order of 10 to the minus of 2, 10 to the minus of 3, so very close to 1. And these are others, let's say, this part gives you the perturbation along the vertical axis, right? So again, you have the possibility of having these non-dissipative dynamics by construction in a different way compared to the residual echo step network. The residual echo step network concentrates the eigenvalues around the unitary circle, or let's say close to the unitary circle. In this case, we concentrate on a vertical line close to 1 on the real axis. And in this case, what we could find is actually that the performance of this system, Euler State Networks, is very good, especially on time series classification. Because on time series classification, you want to let's say, carry in your state the information maybe related to the whole time series, not just a part of the time series, right? Not just the last part of the time series, or maybe only the beginning of the time series, etc. You want to carry information about what happened across the whole time series. And this kind of systems, the Euler State Network kind of systems, are exactly capable of doing this, even better than residual echo state networks, and let's say can give you kind of 50% boost on classification time series on average compared to conventional reservoir computing systems. And the last system that I want to mention in this narration, right, is the Reservoir Memory Network. This is another line of work that I performed with Andrea Chen here at the University of Pisa, and this was published last year. Essentially, in this case, what we want to do is like a modular recurrent neural network, and a modular system that tries to avoid the competition within the same layer of two different requirements that are nonlinear processing of time series and memorization, right? Because we can construct, let's say, a system that has a very good memorization ability already without learning And we can we know that we can perform fading memory operations or even non-dissipative operations on top of that. Why not to use two different systems, one for the memory, one for the nonlinear processing? And this is exactly what we do here, because we have a dual reservoir system. We have a linear reservoir memory cell that provides long short-term memory across the input time series, and on top of that, we create a nonlinear. We use a nonlinear reservoir, which can be a conventional nonlinear reservoir, right? Okay, so the difference is that this is not just hierarchical, because the input, the external input, goes to the linear reservoir memory cell, but also to the nonlinear reservoir cell, right? And the nonlinear reservoir cell is fed by both the output of the linear reservoir memory cell and by the external input. Okay, so the memory cell here in this work, we modeled like, if you remember the cycled reservoir that I mentioned at the beginning, then we do exactly this here. So we create a cycled reservoir where the spectral radius is exactly equal to 1. So we have this organization of the eigenvalues of our system, and this system is linear to maximize short-term memory. And for the nonlinear reservoir, well, you can use whatever you like a leak integrator echo state network, an Euler state network, or any variant, even a residual echo state network, right? You can put any variant that you like. But the point is that the equation here now is modified in order to include as input to this nonlinear reservoir also the output of the memory cell, right? Okay. All right, so interestingly, when we compare the performance of this kind of system with echo state networks and in general other reservoir computing neural networks, the performance that we can achieve by this dual reservoir is very impressive, and we tested this in particular to this permuted sequential MNIST, which I don't know if you're familiar with. It's like probably you know MNIST as a dataset, which is very popular. You want to classify, let's say, images, very small images that represent digits. In this case, the images are transformed into one-dimensional time series where you can see one pixel at a time. So one pixel, then the following one, then the following one, etc. And then, so the point is that at the end, so when you see the last pixel, you want to see, you want to classify the original image, right? You want to say what was in the image, right? So this is a very challenging task for recurrent neural networks, because you need to carry all in the state in the last, when you see the last pixel, which is the last time step for your sequence, you want to remember basically everything else about the sequence, right? The rest of the image that you've seen until that moment, right? Compared to conventional reservoir computing, you can have like 10% more accuracy with these reservoir memory network systems. And if you scale these systems to a number of trainable parameters that is close to the number of trainable parameters that you can see in recent recurrent neural networks applications, then you can see that actually you can achieve a performance that is very close to the highest performance that you can have in the literature, right? So the idea here is that this reservoir memory network, without learning in the recurrent connections, but with this smart organization of the state transitions, can be very competitive also on challenging tasks for recurrent neural networks. And the message is that you don't need actually to do extensive training, especially in the memorization part, to achieve a performance that is close to the state of the art in complex tasks, right? Okay, and the work that we are performing actually in these weeks and months is actually related to even a broader generalization of the echo state network approach that we call the echo state network version 2, where we use, in this case, tricks of the state space model from the state space model literature in order to parallelize the training also across time steps with recurrent the recurrent reservoir in an echo state network, boosting the efficiency, and also the possibility of propagating across a lot of time steps the input information. All right, this was my last bit of information for this talk, and I would just like to close my talk by informing you that we will be hiring soon within this Marie Curie doctoral network that is called MindNet, about a neuromorphic computing and signal processing training network. The project will start in January, and the PhD related to this Marie Curie doctoral network will start around October 2026. And the project that we will be performing in Pisa is exactly related to this idea of long-range propagation with reservoir computing, but with hardware-friendly implementations of the concept. So far we don't have hardware implementations of these ideas. We have only software libraries that perform this kind of computation. And we will also like to have hardware-friendly versions of it that can go in, let's say, a form of computing that can be considered neuromorphic or morphological. Okay, this said, I thank you a lot for your attention. These are a few of my references if you want to. Of course, we are very open to collaboration, so feel free to drop me an email or to check our latest results on LinkedIn or on my webpage. And of course, I will be available now for questions, but also, like I said, in the future to collaborate. Thank you so much.
Thank you. Thank you. Yeah, thank you so much for that. That was really, really interesting. Anybody have any questions they want to ask?
Thank you. A lot of questions, really interesting. Can you hear me well?
Yes.
Yes. Maybe the first one about the residual networks. I'm curious about the alpha here. So you say basically with the alpha 0, right, this kind of term moves away, it's a standard reservoir. But then the maximum value is 1, is that correct? Or is it going to get higher there?
The maximum value that you can have here is 1. Yes. You're right.
So it would be again on the edge, would be just
exactly.
Right on, okay.
Exactly.
And is this something that is different for different kind of tasks, or is it always good to have it at 1, or what is the intuition here? What is a good value for this alpha?
Yeah, the idea so far, my understanding is that whenever you need, whenever you want to process very long time series in a non-dissipative way, so you know that from your problem, you need to propagate information across a lot of time steps, you should use a very large value of alpha, close to 1. Mm-hmm. Rather, if you know that the memory that your network should carry about the input sequence is rather short, because this can also happen, then the value of alpha should be, and also beta, should be smaller, right? Ideally here, you can achieve a conventional echo state network if you put alpha to 1 and alpha, yes, to 0 and beta to 1. Okay, yeah. This corresponds to a conventional echo state network. And in that case, again, you need to look in the eigenvalues of this WH. So again, the idea is that here you can change it's more easy to parameterize the system in order to have this propagation across a lot of time steps. And in our understanding, when you want to tackle, let's say, more complex problems in general, this is not, let's say, always the case, but most often, when you want to carry very complex problems, maybe in the area of speech processing or language processing, whatever, you want to have a longer memory, right? So you want to use a value of alpha that is close to 1.
Okay. And then if I might have a second question, for the Euler State Networks, so if they're on the board of stability, can you use still feedback loops externally, right? Not just like a readout, but feeding the readout back into the system, or does it then become unstable?
Okay, this is a very interesting one, really. Thanks a lot for the question. Actually, has not been studied under that perspective so far. That would be very interesting because it would add another term inside of this equation here, right? And okay, or equivalently here. So here the point would be that you would be non-dissipative also in terms of your previous outputs, right? This would be the behavior of your system. Well, if my system is like is operating in self-sustained way, right? So I disconnect the input and I connect only the output back into the reservoir, which can be the case in some applications. Then it would be exactly as formulated here, but X is not the input, is the output, right? Yeah. In the previous time step. So that would already work in this way. But if you want to have both input, external input, and the output from the system back into the reservoir, that would require a different equation, but a very tiny modification of the equation. The point here, in my opinion, is I don't know if you want to do this. At the moment, I cannot imagine an application of this concept. But maybe it's just because I am more into the idea of using this for classification of time series.
I can tell you when we do it in robotics, right? So when we use the body, so if you just have to read out the class of and you have like a spectral radius below 1, then you have this Fedde memory property, and then the only thing that you can learn is basically is one equilibrium point that exponentially fading, right? So you have just one. If you want to have multiple kind of points or limit cycles, then you need this kind of feedback loop.
Yes.
Then it makes sense. So this is basically overcoming the fading memory by sustaining it, by pushing it in one part of the state space and keep it there, and then still have something going on there. Still fading memory, but it's ending up in a different point, basically, or on a trajectory, basically. So that's where it's interesting for us for transitions between grasping and locomotion, for example, or having bifurcation in general implemented. So that maybe that's not important for speech recognition particularly, but for control, that's definitely something that is interesting.
That's a very interesting point, in my opinion. What I would do in that case would not, okay, as this kind of systems that operate exactly at the edge of stability, they will have a very long memorization, but not a type of short-term memory. The short-term memory of this type of systems would be like close to 0, right? Mm-hmm. But they will recall the information, let's say, they will remember the inputs, or in that case, the previous outputs, kind of without limits in the future, right? So I would not use these systems alone, but maybe a nice thing to try would be to have, on the one end, like a conventional reservoir computing system, and on the other end, let's say, like you have two systems that work together, right? So one would be an Echo State network, or something that can be with fading memory, and also something that has no fading memory, like this one, right? Mm-hmm. And so you would construct, let's say, a short-term representation of the input or the output, like you said, but also informed by a very long memory, long temporal spanning memory over the past in this Euler reservoir. So I would use the two systems together. At least I would explore this line of creating the internal recurrent parts, right? Not Euler alone. My intuition is that would not work very well for robotic kind of tasks. But if you use both a dissipative system and a non-dissipative one together with that, then you can boost the performance on the application that you were mentioning. So maybe this could be a way to go.
That's an interesting point, because we combine them with the feedback loop, right? Because when we have physical systems, you almost get fading memory for free, right? Because energy is lost through friction, whatever it is, right? So it's quite a natural way to have a system like that. and then but you don't have this issue, and then you could build it up by having these two components, while we with the feedback loop have both, right? It's a bit like you shift the bias of the system in a different state space, and you can do that by having two systems and have two independent kind of control parameters to move them around. Okay, that's really interesting. Thank you.
You're welcome.
Yeah, so I have two questions. Can you hear me?
Yes.
Yeah. So the first one is, this kind of residual formulation through time seems to be beneficial for trained recurrent neural network too. Have you explored using this formulation for training a neural network instead of just using it as a untrained layer?
That's a good question. No, we actually haven't, and that's a good point. We should. We should actually, yes. We still haven't done so though, and I actually when we came with these ideas, we were not aware of any fully trainable version of this kind of systems, but we were motivated by some works that we have seen in the past to try to understand the behavior of ResNets in the case of very large number of layers, and to study even that kind of convolutional neural networks from the dynamical system perspectives. And then we understood, well, actually, we can do exactly the same for recurrent neural networks and try to overcome the limitations of the fading memory, no? Because in the convolutional neural networks, dissipation means that the layers at certain point will not carry proper information about the image that is at the beginning, no? But here, no, it was a different kind of thing, similar in the intuition, in the initial intuition. After that, actually, I'm not aware if there is something more recent in the literature that starts from these concepts of the residual temporal skip connections with learning, but it would be very flexible. Also, actually, it would be very, very, very useful for avoiding vanishing of gradients. And now that I think a little bit more, there is a version that is, you can say it's a kind of fully trainable version of this system. It's called, ROARN, which is a paper that appeared last year from Andrea Ceni. And maybe we can get in touch later for sharing the full paper. But it's, if you're interested, but it's not like exactly this kind of idea. It's a recurrent neural network where actually you do the training of the internal parts here, and you leave untrained this orthogonal component, and these alpha and beta are actually not the same as here. They are in a convex combination, so it's like alpha and 1 minus alpha or something like that. So there are some utilizations of this approach also in the case of fully trainable systems, but not the full power of it. Not the full power of it.
Okay, that's very interesting, because intuitively for me, because residual network helps with this might
also because here, if you have orthogonal connections that are fixed, then maybe you can have a lot of possible orthogonal matrices, right? Now there's just one way of having an orthogonal network, an orthogonal matrix, and maybe you can parameterize in a different way, no? Especially when you focus on the possible location of the eigenvalues. No, you can have, for example, here you have a spread of the eigenvalues across all of the unitary circle, but maybe you want to focus on a specific subset of the angles, because maybe the length is the same, no? So still have the same property from this perspective, but the angles are different, and the angles can be important. So so far we have this idea that the angles are very important, but still we didn't come with a way to fully train. In the state space model literature, there are ways to train and to parameterize the training exactly to adapt the angles of your system. But that in that case, it's a linear recurrent layer in a sense. So it's a bit different. Yeah, I would be curious to fully train both these WH, WX, and B, but also the angles of these orthogonal metrics. Yeah, sorry for being overlong here, but I think that, I mean, I was triggered to remember this idea about the angles, which is, I think, very important for different type of applications and different type of problems.
Okay, cool. Thank you.
Second question.
Yeah, I have a second question. So I remember earlier in like the reservoir computing, how do we like apply it? One way is like to use like a system of like damping and springs. Is there like an intuitive like way to do this for robotics? For example, using like a physical system that's not a computer.
Sorry, can you repeat the last part? I couldn't hear properly.
Similar to this, do you have like a similar formulation for like morphological computing for the residual network?
Okay. No, we still don't have. We are working on other variants of this approach. Essentially, what we want to do is to create a physical system of this one. And this is a work that is being performed in collaboration, like I said, with the group of Cosimo della Santina in TU Delft. Actually, you don't have these residual connections, but whenever you do, I mean, you start from the ODE version of your system and you do the forward Euler discretization of it, which is exactly what we do here, right? We start from these smaller equation here, and we end up with these two lines on the right part. Whenever you do that, you have this kind of, let's say, you can call it a skip connection from the past, which is like Z time step K plus 1 is something that depends on the previous version of it, plus something else, right? Then you can see this like, it's not actually a residual connection in the sense that I mentioned previously, but I mean, can be generalized in order to go in that direction, right? Very easily, because here it's like having an identity matrix and then alpha equal to 1. The identity is orthogonal as well, but I mean, it's a very tricky orthogonal matrix. So we don't have like residual random oscillator networks so far. That could be a possible line of a possible extension of this work, but for the moment we are more focused on creating a version of this one that can be implemented actually in the hardware with the springs.
Add something here. I think it's a really interesting question, and maybe because when we tried it with the robots, with the soft robots to implement this kind of things, we were surprised that it worked, because in the classical echo state networks or liquid state machine, you have this kind of almost full connectivity, right? And so we weren't sure if that constraint is too strong. We were surprised that it worked. But one thing is that also, if you look at the theoretical underlinings to prove that it works, right? There's a step where you separate nonlinearity and memory. What you do basically with we call it Reservoir Memory Network, right? Where you separate them out. And something that you can think about if you talk about robotic system is that maybe we can make the separation between neurological side and morphological side. That you say, okay, the brain is really good for long-term memory, the body is bad in that, right? But it's the non dynamics, it's really easy to implement in the body, but maybe more complicated in the neurons. So maybe that is a way to separate it, right? So not everything has to be in the body, but with the brain together, and have different layers and work together. I think that's one way to think about it in robotics.
Yeah. This is also very interesting and very close to what we are trying to do with this modular take on reservoir computing, right? I mean, some parts can be implemented maybe, I don't know, more easily in photonics. Other parts can be implemented more easily in memoristic devices. Why not to put all of these things together, for example? Yeah. Well, essentially, yeah, there is a lot of work that is possible, and especially at the intersection now of the areas now that we're working as computer scientists, and of course our competencies now in the physical part of it are very limited. And yes, I really appreciate these initiatives, as you Helmut, you know, and I really would like to be in touch in the coming months to possibly explore synergies and possible maybe to see maybe how it's possible to implement in physics and to see the physical laws performing this kind of computation on non-dissipative form of computation would be very amazing, really amazing from my perspective.
Yeah, same here. I think having like a reservoir computing over like body and brain, right? That would be really interesting. So you build full machines who are all based on reservoir computing. That would be interesting, for example. Yeah, definitely. We are staying in touch, and you should also follow up as well. I think you have really good ideas, and I think you should talk as well. Yeah.
Yeah. Absolutely.
More questions? If not,
Is that everything? Yeah.
Thank you so much for doing that.
Yeah, thank you so much. It's been really good. Yeah.
And enjoy your wedding and your honeymoon.
Yeah. Thank you. Yeah, been in honeymoon. I came last week. It was like a pity to come back.
But I see. I thought you were going afterwards. Sorry, yeah, done. Okay, congratulations.
Yeah.